Evening to everyone. So we are here for the PhD defense of Vishakha Patil. If I remember correctly, this is the fourth time she will be giving either a colloquium or a defense. She started in 2017 as an MTech research student, and she wrote a paper in JMLR, which has already garnered more than 100 citations on fairness in multi-armed bandits. And then immediately after submitting her MTech research thesis, she continued for PhD. And over the last 4.5 years, has done some very interesting work exploring fairness and causality issues in general online decision-making problems. And some of you, I think, have attended the colloquium also, but I'm sure she will make it interesting for those people who attended the colloquium as well. And I would like to brag about myself also. She happens to be the 28th PhD student who is giving the Viva. Yesterday, Amal Roy was the 29th and my last PhD student who gave the colloquium. So I have some bragging rights. And on that note, let's give a wide applause to Vishakha. Invite her to give it.
Thank you, Professor Narari, for the kind introduction. And thank you, Professor Mallikarjun Rao, for agreeing to be my thesis examiner. Yeah, coincidentally, Professor Rao was also my MTech research thesis examiner. So so my thesis work is broadly centered around fairness and causality in online decision-making settings. Before going ahead, I would just like to thank both my advisors, Professor Narari and Professor Arindam Khan, for being super supportive over the past several years and for their guidance. And I would also like to thank all my collaborators without whom this work would not really have happened. Typically we are always faced with this explore-exploit dilemma in many real-world situations. For example, consider when we want to decide where to go out for dinner, and maybe you have one place where you've been to fairly often and you know what to expect, and on the other hand, you have this fairly new option where you don't really know what to expect from the place. So when you have to repeat this decision over time, how do you decide between the two over time? A bit more abstractly, we can think of these online decision-making settings as this interaction between an agent and an environment, wherein the agent takes some action, the environment responds with an observation and a reward. And the goal of the agent here is to maximize the reward. So suppose this environment was stationary, that is, say there were n actions and each action just corresponded to a deterministic reward, then there's nothing much interesting. You just cycle through each of the action and at the end of n rounds, you know what the rewards are and there's nothing left to learn. But things are rarely this simple. So we look at some decision-making models with uncertainty in them. One of the models is this multi-arm bandit model, wherein you have a set of actions. The agent is faced with a set of actions, and each action has a corresponding reward function, which could be either a probability distribution or something such. And the agent has to decide an action to choose or an arm to pull at each time, with the objective of maximizing its long-term reward. Another popular model is what are called Markov decision processes, which can be thought of as a generalization of the multi-arm bandit problem, wherein there are several states and each state can be thought of as a distinct multi-arm bandit instance. And at any point of time, the agent sees that it is in a particular state, decides which action to take, and depending on the state action pair, it obtains some reward. And also there's a probability with which it will transition to some other state. So both these models have fairly wide applications in the real world, ranging from applications like online advertising, job recommendation, homepage optimization, and crowdsourcing. We will focus on two of these for now because those are more pertinent to the models we look at. So looking at crowdsourcing, a typical scenario is there are a set of crowd workers, and the decision maker wants to allocate some tasks to these crowd workers over time, and all that they want is the task to be done with high quality. And the question is, which of these crowd workers do we assign these tasks to? So for example, I think this is pretty apparent. So studies have shown, and I think it's pretty apparent that with more number of repetitions, your performance at a given task improves over time. And with such a performance, the question is, how does the decision maker decide which which crowd worker to assign the task to? Coming to this second application of homepage optimization, for example, Netflix, when it recommends a movie to you, there are various factors which it can decide upon, such as which image to show, what description to show with it, and whether to give you any offers along with it. And each of these is going to determine in some way whether the user actually watches the movie, which is all that is of interest to Netflix. And I'll go ahead and show how these can be modeled as one of our online decision making frameworks. So my thesis broadly focuses on two themes. One is of fairness, the other of causal inference in online decision making models. Primarily focusing on fairness first. So during my MTech research, we worked on this notion of quota-based fairness in the stochastic multi-arm bandit problem. One key thing to note here is the stochastic multi-arm bandit problem is inherent stationary in nature. That is, the reward distributions do not change with time. And when we are talking about fairness, most of the time the decisions affect people, and which is likely to cause an evolution in the underlying characteristics of the population. So there's a need to consider non-stationarity. So in this thesis, we looked at two ways of modeling non-stationarity. One is via this model called improving multi-arm bandit model. The second one being Markov decision processes. And under the theme of causal inference, we looked at this variant of the multi-arm bandit problem called the causal multi-arm bandit problem. So I will first go through the details of the fairness in improving multi-arm bandit model. So this work is a joint work with Vineet, Ganesh, and Arindam. So going back to this application that I spoke about a bit earlier, consider this crowdsourcing platform wherein there is a set of crowd workers, and the decision maker has to decide which of the crowd workers to assign a particular task to, and this has to repeat over time. So now look at these two reward curves corresponding to two different crowd workers. And say I'm the decision maker and I have to decide which of the crowd workers to give a task to. Say one natural thing to do is to give one task each, see how each of them perform, and then finalize on the one doing the task better. But given that our learning curves follow such a pattern, there's no way for the decision maker to know that maybe the person who is performing slightly worse now may go on to perform much better given more opportunities. So the question is, how does one decide, even just from the perspective of, even without going into fairness, even if we just look at reward maximization or performance maximization, it's not very clear how do we decide how to do this allocation. Okay, so now if we look at further fairness here, what happens is, say we decide, so because these arms correspond to, so these curves correspond to people, we would like to also be fair. Say if we just follow meritocracy, again, what will happen is we will soon decide that, okay, the red arm seems to be doing better than the blue arm. So always favor the red person corresponding to the red curve. And so that will lead to like the blue curve not being explored enough. Similarly, the other notion of fairness in the bandit literature, which is quota-based fairness, which is fixed quotas, that may lead to suboptimal performance over time. So we look at first we'll look at how to map this to a multi-arm bandit problem, and then go ahead. So for the multi-arm bandit problem, we map this number of opportunities to number of pulls of the arm. Each of the reward curve gets mapped to an arm of the bandit, and the performance corresponds to the instantaneous reward of the arm. So now the question that arises is, so okay, the fairness notion that we look at here is not an explicitly defined constraint, but all that we want is that an arm which has the potential to improve, we don't stop pulling that arm, at least till it reaches its true potential. And again, it's if you couple this with the goal of maximizing reward, it sometimes looks like these two objectives are at odds with each other, but they in fact turns out to be not the case, and I'll get to that a bit later. So to be a bit more formal, an instance of the improving multi-arm bandit problem is defined as follows. K is the number of arms, and Fi is the reward function of arm I, where Fi of n is the instantaneous reward for the nth pool of arm I. We make two assumptions on the reward functions, and this is justified by our motivating examples of human learning curves. So one is that it's bounded. This is required to give any meaningful guarantees. We don't really need 0,1, but any constant is sufficient. The second is that they are monotonically increasing with diminishing returns. This is essentially motivated from our examples that we look at. So now here the goal is to maximize, even without fairness, the goal is to maximize the cumulative reward in t time steps. And how do we define the cumulative reward? This is the expression. So I sub t is the arm pulled by the algorithm at time step t, and NIT at t is the number of arm pulls of arm IT in those many time steps, and the reward is just the cumulative sum of these values. So even before going to the algorithm, the question that arises is, if we knew the instance and the time horizon beforehand, what is the best one could hope for? So essentially what we are asking is, what is the optimal offline policy here? So it turns out that the optimal offline policy here is to play a single arm, and it is the arm which maximizes which has the highest cumulative reward for t time steps. So intuitively, you can also think of it as the largest area under the curve. And so that defines our optimal arm for capital T time horizon. One thing of interest here is that in this particular problem, uh, even if we knew the instance I beforehand, the time horizon plays a crucial role in determining the baseline. Because if assume that your time horizon is capital T1, then it's clear that the red arm 1 is better of the two. Whereas if your time horizon shifts slightly ahead and it's slightly greater than T2, then arm 2 could start being the baseline. Now the question is, how does an algorithm which does not know the time horizon beforehand be competitive with respect to any of the shifting baselines as your time horizon increases? No, here we don't. Yeah, it's just instantaneous summation. Yeah, so the evaluation matrix that we look at, so we already defined the optimal policy. This is the reward of the algorithm. So we look at two notions. One is the regret, which is just the difference between the optimal and the algorithm. And the second is the competitive ratio, CR, which is just the ratio of optimal to algorithm. The first result we show is a lower bound on each of these quantities. And it turns out that you can't really hope to do much in terms of the regret, which is lower bounded by some constant times capital T. And the competitive ratio is lower bounded by k by 2, where k is the number of arms. We prove this by considering a family of instances. So we construct a family of k instances, and a particular instance IM looks something like this. So we have m arms, so all the arms will have the same reward function up to time n, or up to number of pulls n. And at that point, one arm continues to grow linearly and then reaches 1 and flattens out at t, where all other arms flatten out right at n. And by considering k such instances, we can prove this lower bound. Whereas, yeah, the competitive ratio is lower bounded by k over 2. Now, again, coming back to, since we study this problem in the horizon unaware setting, coming back to why knowing the horizon becomes crucial here and how it can be leveraged. So, okay, so suppose we've pulled an arm n number of times. So we know the slope of the curve at between these 2 points. Now the thing is, okay, so what we can do is, because of the properties of the reward function, which is increasing with decreasing marginal returns, we can get an optimistic and pessimistic estimate of how this curve can increase. So I know that no matter what happens, if I continue to pull this arm for the remaining rounds, this is the worst it can do and this is the best it can do. And it has to be somewhere between these two extremes. Now, if we know the time horizon beforehand, what we can do is at some point there is an arm I whose optimistic estimate is less than the pessimistic estimate of some other arm, we can just stop pulling that particular arm I in this case. But when we don't know the time horizon beforehand, we don't really know how much to extrapolate these quantities for, thus not giving us the same benefit. So what we do in our algorithm instead, and this is just a high-level idea, is we take a proxy for this time horizon. And in our case, it is n star, which is the maximum number of arm pulls that any arm has received till that point. And we compute an optimistic estimate up to n star for each of the arms. And then we go back to this old friend of ours from the bandit world, which is optimism in the face of uncertainty. And we just pull the arm with the highest value of this optimistic estimate of cumulative reward. And it turns out that yeah, so this particular choice of n star has lots of interesting properties. One being that one of the things that it guarantees us, and this requires a proof, is that the first arm to cross n pulls is actually optimal for if the horizon had been capital N. So this, with a lot of other intermediate results, gives us this final result wherein we can show that the competitive ratio of our algorithm is actually order k, that is, it matches the lower bound up to constants. And the second thing we show is that given sufficient time, the proposed algorithm will ensure that each of the arms reaches its true potential, which also means that it will never stop pulling an arm which has the potential to improve. Now, this by itself may not be an interesting property because even like round robin satisfies it. But given that we can satisfy this while ensuring optimal reward is what makes it interesting. Yeah, that brings me to the end of the first work. If there are any questions.
I have nothing right now. I'll ask you
Yes.
at the end.
Okay, sir. Yeah, so if we did not, we will have to assume something because without that, yeah, but we don't really know what. Yeah. Mhm.
Once the potential is reached, rather flat.
Okay.
Like competitive ratios are rigorous as a function of the AD and the.
Okay.
I mean, both in the lower bound example, you do have the high values. They are actually linear.
Yes. Yeah. Yeah.
So in a concave sense, they are as concave as
Yes.
before. But like, so like strongly concave or something that does flatten out. Yeah. So
Okay, yeah.
like log families or something like that.
Okay.
So more
Not-
concave than linear. Yeah. Okay.
Yeah.
Okay. But even if you have like bound on the gradient or something, like even the special classes like yeah. Bound on gradient.
Okay. Yeah, the second work is on fairness in Markov decision processes. So this is a joint work with Ganesh, Vineet, and Yilun. And here we are motivated by settings wherein mostly resource allocation settings, and wherein the dynamics of resource allocation are governed by a Markov decision process. So to give a very simplistic example, consider a server and two clients, and the clients like submit jobs to the server for processing. And we can model the system as follows. So the state captures the number of jobs of each client that are pending. So N1, N2. So N1 is the number of jobs of client 1 and N2 is that of client 2. And an action is just the number of jobs that will be processed for that particular client. And new jobs are assumed to arrive stochastically. And the total reward looks something like this, which is M1 times R1 and M2 times R2. And R1 and R2 are client specific. Sorry. Yeah, so what could happen here is that the server could end up prioritizing jobs of the client which pays higher. But in situations like this, we would also like to guarantee some minimum quality of service to each of the clients. And these are the kind of settings we are interested in. And given this modeling, we can achieve such kind of fairness by ensuring, like, requiring that certain states be visited some minimum fraction of the times, especially the states which have low values of N1 and N2. So yeah, in the MDP model, our fairness constraints look like this: to visit each state some pre-specified minimum fraction of the times. And yeah, this has to be independent of the expected rewards of the state action pairs. And the goal is to maximize average reward while satisfying the fairness constraints. So a typical MDP instance looks like this. S is the set of states, A is the set of actions, you have a transition probability matrix, a reward function, and an initial distribution. For the fair MDP instance, we also introduce this vector rho, which captures the state visitation frequency. So rho of state S would be the frequency with which we want state S to be visited. In the sense, I did not get you.
Maybe I'm jumping.
Yes, yes, yeah.
It's stable.
Yes, yeah. So yeah, we do. We assume that the MDP is ergodic, and so yeah. So given a policy pi, it will induce a stationary distribution denoted by nu pi, and we say a poly. So given a rho, which is the fairness constraint vector, we say that a policy pi is rho fair if for all states S, nu pi of S is at least rho of S. So yeah, going back to our goal. So the evaluation metric we use here, because we have these two objectives of satisfying the reward, we want to be as close to the optimal reward as possible while also satisfying fairness. A policy pi is said to be epsilon 1 approximate and epsilon 2 fair if the reward of the policy pi is within epsilon 1 additive factor of the optimal policy, and nu pi point-wise is at least rho minus epsilon 2. So what was known so far is that, so Jin and Sidford had proposed an algorithm that computed a policy that approximately satisfies linear constraints, which are a bit more general than the constraints we are looking at. But they provided no guarantee on the reward. So all that they gave was a feasible policy with no guarantee on the average reward. The way we approach this problem is to formulate the fair AMDP problem as a bilinear saddle point problem. And we assume that we only have sample access to the model. So for this, we use stochastic mirror descent to solve the problem. And what the policy that is output by our algorithm, which is pi epsilon, is 3 epsilon approximate and epsilon fair in expectation. Yeah, so this, to our knowledge, this was one of the first works to provide a simultaneous guarantee on the constraint satisfaction as well as the reward, while also providing sample complexity bounds. Yeah, this brings me to the third work. Yeah, we also have a bound on the convergence time sample. Yeah. Okay, so I'll proceed to the last work, which is on causal bandits. So this is a joint work with Vineet and Gaurav. So going back to an example we discussed earlier about how to optimize the homepage for a service like Netflix. So there are several factors which are under the control of the decision maker, which is sort of to decide, say, what image to show, what description to show along with it, whether to offer some promo code to, watch it at a discounted rate and such things. These factors could have an impact on whether the customer goes back and checks the reviews for that particular show, which is directly not under the control of, say, Netflix. And all of this eventually has an impact on whether they actually watch the movie or not. And this is ultimately what Netflix would be interested in. So the question is, how can we choose these factors in a way that the reward the reward, that is the probability of watching a movie here, is maximized. So this can be captured in the causal bandit setting. So particularly this particular structure can be captured by a causal graph, wherein each of the nodes of the causal graph is a random variable, and we assume that there is a joint probability distribution over these nodes. And there's a special node Y, which denotes the reward node. Now, in a tip, like one thing you can do is just observe, that is some of these, like the nodes get sampled from this underlying distribution, and you observe the values that each of the node takes. The other thing you can do is intervene on this graph, which is certain nodes, you can intervene on them by setting their values explicitly. And what this does is to sever all the incoming edges into that particular node, and it defines a probability distribution over the remaining nodes, which are not intervened upon. And now the goal is to find the intervention that maximizes the reward. So this can be mapped, so there are variants of this. So there could also be budget constraints here, wherein, say, going back to the example of Netflix, the interventions could be more expensive compared to observations, because you explicitly need to go and make changes to the system. And there is this trade-off between observation and intervention here. And one of the key questions is, can you learn something about the interventions from the observational data? So to first model this as a bandit problem, we assume that the causal graph G is given, and the set of allowed interventions is also given. We do not know the underlying probability distribution. And we have this special intervention, which is to do nothing, which is essentially observation. And we model this set of allowed interventions as the arms of the bandit. And the goal is to find the intervention that maximizes the expected reward. So the expected reward of an intervention A, where A looks something like do of x equal to small x, wherein x is a set of nodes and x would contain the values that you're setting them explicitly to. And mu of A is the expected value of y given do of x. And our goal is to find the one with the highest intervention with the highest expected reward. So the cumulative regret in this setting, wherein we do not have a budget constraint, looks similar to almost the same as that in a stochastic bandit case, wherein the arms are the interventions. So you just take the max over all arms. This is your optimal in hindsight, if you knew the mu is beforehand, and you play that particular intervention for all capital T rounds. And 8 sub T is the intervention you performed at time step T, and mu 8 is the expected reward of that intervention. And the regret at time T is just the difference between the two quantities. So for this problem, the causal bandit problem without any budget constraints, and for general graphs, what was known is this regret bound on the cumulative regret, which is order root k to the power n times t, where k is the distinct number of values that each node can take, n is the number of parent variables of the reward node, and capital T is the time horizon. And this was under the assumption that the distribution of the parents is known for all interventions. So with the same assumption, and with one small additional assumption, which I've not mentioned here, we show that we actually prove a constant regret in terms of instance dependent parameters. And idea is pretty much like this algorithm is also a UCB based algorithm. We also give a UCB based algorithm for this. The only one of the key differences is what is the quantity for which we maintain a UCB estimate for. So slightly switching gears, we come to causal bandits with budget constraints. So here interventions are assumed to be more expensive than observation. And the goal is, can we learn something about the interventions from the observational data? So say without performing any intervention, we observe x3 equal to 1. We would like to use this information to learn something about the effect of do of x3 equal to 1. So in this case, we study this problem both with the goal of minimizing simple regret and cumulative regret. So the cost, so okay, assume that the cost of observation is equal to 1 and the cost of intervention is gamma, which is greater than 1. And assume we have a budget capital B. Now, what I want to do is I want to run an algorithm which will either observe or intervene, but within this budget B, and at the end of and when I run out of my budget, I want to output an intervention saying that this is the best intervention. So that is captured by A sub B here, which is the intervention output by the algorithm, and this is the this is the optimal, and this is the simple regret. So for this, we provide an algorithm. Okay, first thing to note is that if this, we show that if this gamma is greater than 1 over, so these are all instance dependent quantities. So we show that there is a threshold such that if gamma is greater than the threshold, then it's always better to play the observational arm. And otherwise, if it's not, then it's we devise a policy with which to play the arms. The catch is that we do not know, since this depends on the underlying probability distribution, we do not know them beforehand. So the idea is, how do we estimate these quantities online and do this balancing between observation and intervention? So for this, we provide an algorithm which does this estimation and does this trade-off online and decides between observation and intervention. And we provide this guarantee. So if, say, in this instance, gamma is greater than this quantity, then we have such a regret guarantee. Again, many of these quantities are instance dependent, and I won't define them for now. And if gamma is less than this, then this is a regret guarantee. Now, in this case, we also have a lower bound which follows from another result in a paper by Latimore et al. And that holds here, whereas we do not really know whether this is optimal or not. Oh yeah, sorry, I forgot to mention. So this is with the no backdoor criteria. Yeah, sorry, yeah. So yeah, these results only hold for a class of graphs called no backdoor graphs and not for graphs in general. Yeah, sorry about that. Yes, so essentially in this particular work, we provide 3 algorithms. So the first one, CUCB2, is for the non-budgeted setting, which provides a cumulative regret guarantee. Both these algorithms are for the budgeted settings, and the results hold only for no backdoor graphs. And we provide cumulative as well as simple regret guarantee. So this one I did not go into, but the cumulative regret guarantee is order log B in general. And for certain special cases, we can actually show order 1. And the final thing is, this is the other algorithm I discussed, which has this dependence on the underlying probability distribution thresholds. So that almost brings me to the end. So going to the future work, I think in the improving multi-arm bandit problem, there is nice motivation to look at it from other fairness constraint, fairness perspectives also, such as Nash social welfare. Also, other sources of uncertainty in online decision-making models. Lower bounds for causal bandits remains quite an open area. And also, yeah, one of the reasons I started looking at causality during my PhD was to look at fairness and causality together, which never happened, because you can think of these fairness constraints as interventions in a system and to study the long-term impacts. So yeah, I think that is also another interesting idea. Yeah, thank you.